All right, day 97. We all know that machine learning models are hungry for data. But here's the catch. The most valuable data is often the most sensitive. Think medical records or financial transactions. This puts us in a bind, creating a huge conflict between building powerful AI and protecting privacy.
So this leads to a pretty fascinating question, one that almost sounds like a riddle. How can you possibly process data that you're not even allowed to see?
You see, the traditional way of handling this is, well, it's pretty risky. You have to decrypt the sensitive data, do your calculations, and then quickly re-encrypt it. But that tiny moment the data isn't plain text, that's a massive vulnerability. The alternative with homomorphic encryption is much cleaner. You just never decrypt the data in the first place.
And in the next few minutes, you'll understand exactly how we can pull that off. Let's start with the core intuition, and the best way to do that is with an analogy. Think of it as computing inside a locked box.
Imagine you have a totally secure lockbox. This isn't just any box, though. It has special gloves built into the sides, kind of like what you'd see in a science lab. And most importantly, only you have the key.
So here's the process. First, you place your data inside the box. That's encryption. Then, you lock it up tight. Now, you can hand this locked box to someone else. They can't see inside, but they can put their hands in those special gloves and work with what's in there. That's the computation. Once they're done, they hand the locked box back to you. You use your key, open it up, and take out the result. That's decryption.
The most important point in this whole process is that the raw data itself is never ever exposed to the person doing the work. It stays secure inside the box the entire time.
Okay, the locked box is a great mental model. Now let's switch gears and look at the technology that actually makes this possible.
This magic box is actually called homomorphic encryption. It's a method that allows us to perform computations directly on ciphertext, the encrypted data. And here's the amazing part. When you decrypt the result, it's identical to what you would have gotten if you did the math on the original unencrypted data. Now, the most powerful flavor of this is called fully homomorphic encryption, or FHE. This is the one that gets all the attention because it supports pretty much any kind of computation you want to do, which makes it perfect for complex tasks, like training a machine learning model.
So how does it work? It's not magic, just some very clever math. It relies on complex algebraic structures and some pretty intricate algorithms. Most modern systems use an approach called lattice-based cryptography, which is what makes the whole thing work. And as a cool bonus, this technique also happens to be resistant to attacks from future quantum computers.
Of course, there's always a trade-off. Historically, it's been performance. Running computations on encrypted data is just much, much slower. It's computationally expensive. But the good news is that better algorithms and specialized hardware are really starting to close that performance gap, making this more and more practical.
Okay, that's the theory. But where is this actually being used in the real world today?
This technology is unlocking collaborations that were simply impossible before. In healthcare, different hospitals can pool their patient data to train a better diagnostic model without ever revealing individual patient records. In finance, it can be used to run fraud detection on encrypted transactions. And for us in ML, it's a huge deal for training models privately on cloud platforms.
And this isn't just theoretical. Projects like CryptoNets have already demonstrated that you can apply neural networks directly to encrypted data and still maintain high accuracy. So what this all boils down to is that it allows different organizations to work together on sensitive data sets without ever exposing the raw information to each other.
In one sense, homomorphic encryption lets us use data without seeing it. And the key takeaway? Homomorphic encryption directly addresses that core conflict between data utility, the need to use data, and data privacy, the need to protect it.
So I'll leave you with this question. What new problems could we finally solve if data privacy was no longer the main blocker to collaboration?